Our topic for today is sinusoidal oscillator. Let's understand what is a sinusoidal oscillator. Let's say we have an amplifier here. You have studied about amplifiers. So this is a basic amplifier with gain as A. Okay. So there must be input to it. Let's say this is the input and this is the output. Without pointing to whether this input is voltage or current or the output is voltage or current, let's say our input is Xi and the output is XO. Okay. So from here we know that XO means A into Xi. That is the definition of gain. A is gain. So A means A into Xi is XO. Now, let's say to this output we add a feedback network with factor beta. This is your feedback network. So we have added a feedback network. What will be the output? Let's say it is XF. You know, XF will be equal to beta into X output. Okay. Now let's bring this output to this point. Let's not connect it. Okay. So this setup is clear. This is input signal. This is a basic amplifier with gain A and this is the output. Therefore, A is X output by X input. Now we sample this output into a feedback network with factor beta. So the feedback output will be beta into X output. Up to this it's clear. Let's say here we have a mixer which is basically an inverter. It's a mixer or you can call it an inverting circuit. Okay. So what is the output of this? If this is XF, you will have minus XF at this point. Okay. So what is the loop gain? This is loop. What is the loop gain? Loop gain is basically what we have at this output and this as input. So this means minus XF by XI. This is your loop gain. That is, from input it traveled to this, then from output it was sampled by the feedback network and at this point we get minus XF. So loop gain is basically minus XF by XI. And what is minus XF? It is beta X0 by XI. But X0 by XI is A. So this is minus beta A. Okay, clear? That is, if we send Xi, here what we get is minus beta and A. Clear? Very clear up to this? Now, let's say this minus beta A becomes 1. The question is, what if minus beta into A is equal to 1? When minus beta A is equal to 1, it means your minus XF is equal to Xi. That is, this output is equal to this. Clear? Let's say this is X dash F. So you can write this as X dash F by Xi. So when this becomes 1, this quantity, it means this output is equal to input. That is, this becomes this. You started with this point and when you return, if this condition is met, this signal, the signal that you sent is actually available at this point. Exactly the same signal. What will happen at this point? At this point, if you connect this and if the source was, let's say this was our source initially. Now when you start receiving Xi at this point also, you just remove this source, the input. Now whatever Xi that you were getting is actually channeled back from the output and getting back into the amplifier. That is, this circuit becomes self-sustained. You don't need, what is the meaning of self-sustained? This means you don't need any input signal to get the output. This circuit is now dependent on itself only. So from here we have this expression minus beta A is equal to 1. Now this is a condition for self-sustenance of the oscillator circuit. This condition is called Barkhausen Criterion. I am rubbing this. See, what is the meaning of Barkhausen Criterion? First, you saw it is beta A equal to 1. This means the first condition is that from input to output, this oscillation will, you'll have this oscillation only when the phase shift from here to back to this point is phase shift from where? Phase shift from input to output and then by feedback network to this point. When the phase shift is equal to 0 or it is a multiple of 2 pi. At this condition, this condition will be satisfied. Second condition will be that the modulus of this beta A, that is the gain after this feedback network, this should be equal to 1. These are two conditions which are called Barkhausen criterion. That is, phase shift from input back to the input should be 0, either 0 or multiple of 2 pi. And second, that magnitude of this beta A amplification, this should be equal to 1. These are the two conditions. So if these two conditions are met, this circuit will break into oscillation. Okay. Now we'll see what is the frequency of oscillation of this circuit. So this is circuit of a phase shift oscillator using a FET, field effect transistor. These are cascaded RC network, CR, 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 okay, and you can see this is V dash F plus minus. This is fed into the gate, that is at the input gate to source. This is source, see. So at gate to source we have minus VF. You can see this plus has been entered here. So we are feeding minus VF at this point. The equivalent circuit will be, let's say this is your RC network, then equivalent circuit will be like this. Simplified model will be like this. This is, if this is our gate and this is source, we'll have V input that is equal to minus VF, we have used dash. So this is minus VF dash at this point, at the input. Here what you will have, let's say this is your drain D. So at this point you will have this, then of the field effect transistor, this is your RD, this resistor, this is bypassed, okay. So here is your output, this is your output at this across this resistor, this is your output, V output, and to this what you have? You have output, that is your RC network. So I am putting it like this. Let's say this is your RC network, okay, and this is the output of the RC network. This is what? GM into, this is VI, so VI. This is the simplified model of this circuit. So for this to be a sinusoidal oscillator, we had seen that the Barkhausen criterion is beta A equal to 1. The first thing that is required is that the phase shift should be equal to 0 or 2n pi. Now what happens? This amplifier shifts for 180 degree. So that what we do, our RC network, we design it in such a way that the output is exactly shifted by 180 degree. So if this is minus and this is plus, the effective shift will be 0. That is, we will get 0 shift from output to input. Okay, this is the first part. So what we do is that we select such a frequency that this RC network shifts the input signal, which is this V output for this RC network shifts it exactly 180 degree. That is, from here to here we have a shift of 180 degree, and the rest 180 degree shift is in the inverse direction, is in this FET amplifier. So one in positive direction and one in negative direction. Effectively the phase shift becomes 0. So first condition is met, and second condition, beta A equal to 1. We'll see that this is equal to 1. If these two conditions are met, our this phase shift oscillator using a FET will behave as an oscillator. Now let's see what is the value for which, what is the value of the frequency for which this circuit will exactly do this. Minus beta A equal to 1. I am rubbing this. Okay. See, our alpha is 1 by omega RC. What is omega? You know the frequency, 2 pi f. Omega is 2 pi f. Okay, this is the frequency of oscillation. So alpha is equal to 1 by omega RC. Now the feedback factor, this minus beta, is actually given as of this network in terms of alpha is 1 by 1 minus 5 alpha square plus j 6 alpha minus alpha cube. You should keep this in mind. Now what is there? We have V dash F by V output. What we want, because this circuit, this amplifier circuit is giving a phase shift of 180 degree, to counter that 180 degree, what we want is that this should be equal, this should give another shift of 180 degree. So to get that, the value that you require is alpha square equal to 6. Okay. Now if you put alpha square 6 here, what you get? Omega is equal to 1 by alpha RC. So what you get is 1 by root over 6 RC. This is the value of omega. Or if you want F, this will be 1 by 2 pi root over 6 into RC. So this is your frequency of oscillation. That is, if the frequency of the signal that is in this circuit, that is running in this circuit, is equal to this value 1 by 2 pi root 6 RC, that is, we tune R and C in such a way that frequency of oscillation becomes this. What we get? We get a phase shift of 180 degrees through this network, this beta, this feedback network, and the rest 180 degree to counter it is through the amplifier. So our phase shift will be equal to 0. Now to get beta, here you have relation between beta and alpha square. From here what you get, I am rubbing this, if you put this, what you get is beta equal to 1 by 29. So that you know A beta equal to 1 is a criteria. So from here what you get, your amplification should be at least 29. That is, it should be greater than, a bit greater than, and at least equal to 29. This is the condition. So the two conditions are frequency equal to this, A equal to this. Clear? So if these two conditions are met, your this circuit will start oscillating at a frequency which is equal to this. Clear? Now this is another phase shift oscillator using a BJT. The last one that we saw was using a FET, field effect transistor, or you can put MOSFET also there. But this is a BJT amplifier phase shift oscillator. So what is happening here? Try to understand. This is your BJT that is doing the amplification. This is your RC network. See, CR, CR, the way we had there, but we had CR, CR and the next CR. Here what we do, we take this C and then R, through R we put into base. We have input resistance of the transistor here. So R3 and Ri, they are in series, effectively in series. That is R3 plus Ri is what we have with this C and R. So that part is equal to R. So we carefully design the circuit where our R3 is equal to R minus Ri. This is the first thing, so that effectively what we get is C, R, C, R, C, R. Okay, so try to understand this properly. We have to get this CR network only. So what we do, we have C and R, C and R. What happens in a BJT amplifier in this CE mode, the input resistance is low. So if you put series voltage series feedback network in voltage series mode, what will happen? This input resistance will get all the voltages across it. All current will be drawn to it. So what we do, we are using a voltage shunt mode, so that our network is like this: CR, CR, CR. This R is basically this one. See, this R is basically R3 plus Ri. This is only thing to understand. These are resistors for biasing, nothing else. Here also we have Re, and we have a capacitor Ce. It basically bypasses this and we get directly to the ground. So I think this is clear to you, so that we get forward. Now if we take HOE into RC less than 0.1, we can use the small signal model of BJT to analyze the circuit, and what we get is, this is base. At the base you have HIE, okay, and then at the collector what you get is, this is HFE into IB. What is IB? IB is this, IB, okay, you know this figure. And then you have the resistor collector resistor RC. This is the output voltage, and then you have these three CR circuits. First is this one, C into R, then again C into R, and then finally this C into this. That is, I told you, this is actually R3 plus Ri. Okay, this is your I3, that is the output current, and this is IB. So we have to keep I3 by IB equal to or greater than 1. Okay, so this is the simplified model. You can put mesh analysis, you can do mesh analysis and get results. Finally what we get for this circuit is that your frequency is equal to 1 by 2 pi RC into 1 by root over 6 plus 4K. You should learn this formula. K is what? K is actually RC by R. This is the ratio, RC by R. So from here you get frequency. Clear? F is equal to 1 by 2 pi RC into 1 by root over 6 plus 4K, where K is RC by R. This is how you can design the circuit. Clear? And for the second part, this is for which you will have 180-degree shift. The second part, for I3 by IB, I told you, to exceed unity, what you need to get is HFE should be greater than 23 plus 4K plus 29 by K. You know what is K? K is RC by R. So HFE should be greater than 23 plus 4K plus 29 by K. Okay. Now interesting thing is, the minimum value of K that you get for this circuit is actually 2.7, and based on this value, HFE is equal to or greater than, you can say, greater than 44.5. That is, a transistor with HFE less than 44.5 cannot be used for making a phase shift oscillator. So HFE has to be greater than 44.5. So you should learn this. You should keep these formula in mind, and you'll get some data. You can find the frequency of oscillation. Okay.